Welcome into the best in paranormal podcasting. This is Darkness Radio. I'm your host, Tim Dennis. Today, folks, we're going to a scary place, but it's a good place. You know, I've said on this program many times before, I get emails from you guys that say, Tim, we can handle it. We want more science. Well, you know what? We're going for it today, folks. We're going to that deep, scary place. I want you to hang with me. Actually, we have an excellent guest today. Dr. Charles Liu, PhD, is with us. We're going to that place known as quantum physics land, quantum mechanics, because it seems like quantum physics is the touchword. It's the keystone. It's the hot topic when it comes to the paranormal world lately. And this is why you've heard of, and I'm going to talk to Dr. Liu. I don't know. I think it's probably going to be in the second part of the program today about the quantum afterlife, and he may or may not be familiar with it. We'll get into it. We're going to talk about the basics. We're going to start about the basics first of quantum physics, because it seems to be all the rage. You know, quantum physics is not a new thing. Far from. But it's our understanding of it. And, you know, in the paranormal, we like to throw around that we like to do a scientific investigation. I don't think we know, pardon my language, Dr. Liu, our head from the ass in the ground, as far as, or our head from our ass or a hole in the ground. That's what it is, as far as what science really is. So it's my honor today to have an esteemed guest, and I know I'm throwing around swear words in front of an esteemed guest, to have a professor of astrophysics with us to talk about actual science and what the science is and how we can use quantum physics to actually solve some of these paranormal issues. Now, he has a wonderful new book out there. If you actually want to learn about what quantum physics actually is, this book is amazing. It's called The Handy Quantum Physics Answer Book. And you should have a copy on your shelf, because if you didn't learn it the first time around when you were in school, it doesn't mean you can't have it on your shelf right now so that you have it at your fingertips. You should have a copy of this so that you can at least turn to the kids in your life and say, you know what? I have an answer for that. And it's right here. And there's no shame in being able to tell them that. Dr. Charles Liu, PhD, is a professor of astrophysics at the City University of New York's College of Staten Island and an associate with the Hayden Planetarium and Department of Astrophysics at the American Museum of Natural History. His research focuses on colliding galaxies, starburst galaxies, quasars, and the star formation history of the universe. In addition to his research publications, Dr. Liu also writes for students and general audiences, so he can talk to us. I'm just saying, I'm no genius. Including Visible Ink Press's popular The Handy Astronomy Answer Book and The Handy Physics Answer Book, as well as for the YouTube and radio show Star Talk with Neil deGrasse Tyson. I think you guys know who he is. And Jeffrey Lee Simons. For his work with students, he has received the American Institute of Physics Science Writing Award and the Award for Popular Writing on Solar Physics from the American Astronomical Society. Until recently, he served as education officer and trustee of the American Astronomical Society, and he currently serves as president of the Astronomical Society of New York. He earned degrees in astronomy, astrophysics, and physics from Harvard and the University of Arizona, and he holds postdoctoral positions at Kitt Peak National Observatory and at Columbia University. He and his wife have a daughter and two sons, and it is my pleasure to welcome in Dr. Charles Liu. Dr. Liu, how are you today?
I'm very well, thank you. Thank you so much for having me, Tim. Thank you so much for that kind introduction. I think we're going to have a great time today.
I think we're going to have a wonderful time. You know, quantum physics is such a hot button topic these days. It really is. My first question, Dr. Liu, is this. With us throwing that catchphrase out there, or throwing out the topic, and then immediately America being dumbed down, and I'm not going to mince words here. Why is it that we choose to stay dumbed down? Why is it that we see science and then the eyes are rolled back in our head? We get that glazed look in our eye, and we just go, okay, it's just too much, Dr. Liu.
Yeah, you know, you make such a great point, and it's sad, but we can do something about it. In my opinion, after all these years of doing science and being in academia, I'm convinced that we don't teach science right anymore. For the 21st century, We need to treat science in a different way. Right now, we're teaching physics, for example, my fields, and astronomy, almost the same way we've been teaching them since the 1800s. You stack a whole bunch of facts into a big, thick book, or you have someone like me tell you all these things, and then you memorize them and you regurgitate them, and then you wait till the next day, till the next thing that you have to memorize and regurgitate. When we're doing mathematical problems, all we're doing is we're solving them, right? We're learning how to do these puzzles on paper and pencil.
Mhm.
Uh, but in the end, when we're doing the scientific research and we're trying to do stuff, it's really just about asking cool questions, finding or creating the tools that we can do to try to answer them, testing those things that we think might be true and figure out if they're true or false, and moving them forward. And there's a lot of things that we can do with that today that we don't have to go through the rigmarole that used to turn us all off in school about, oh my gosh, it's too much, it's too this, it's too that. If we could get past those kinds of barriers and think about science in general as asking questions and trying to answer them and having fun while doing it, I think we could go a long way towards solving this difficulty that you talk about.
Do you think the other part of it too is that we don't emphasize the play part of science either? Because
Oh, yeah.
there's, it seems to me that when science got thrown at us in school, it seemed like it was too much academia, not enough play. Is that part of it too?
100%. I mean, think about what we do when we're thinking about English,
Mhm.
right? We use English on this podcast to talk about fun things,
Yeah.
or we talk with our friends, we tell jokes, we also write literature and poetry and commentary and things like that. All of it is built in, right?
Mhm.
The English is like the language that we're doing stuff. And so some of us really enjoy jokes and stories and watching people speak on movies and TV shows and stuff, but we really can't get through poetry or literature very easily,
Mhm.
right? Uh,
Yeah. Oh, yeah.
Imagine if those folks were only allowed to think about English in terms of the literature and the poetry that they couldn't get into, as opposed to the literature and the poetry and the art that they could get into. And then you just wind up eventually with this no fun, this isn't any good kind of situation,
Yeah.
right?
Yeah.
It's completely not true, but it's been ingrained in us. I think that we should start teaching physics as a subject to middle school students, elementary school students, so that when they get to the high school part and the college part, and they're seeing here's the technical stuff involved, instead of being like, oh, afraid of it or against it, they're like, oh, that was the game that I played back then. Oh, this is the toy that I use all the time. Let me find out exactly how it all works on the inside. And then I think we would overcome a lot of the problems that we have with science education today.
Well, when you start to read the different concepts in your book, it seems like there's bigger, overwhelming, I shouldn't say over, I'm sorry, not overwhelming. There's bigger, overreaching concepts than like chemistry. In chemistry, you're breaking down minutia,
Right.
and there's bigger, overreaching concepts in quantum physics. So are we why are we not putting that before chemistry? Why is chemistry one of the first things we learn in biology? And
Mhm.
why are we putting quantum physics and physics at the end of the curriculum? Why is it backloaded, not front loaded?
Tim, you've hit upon an excellent question. Many of my colleagues feel the same way. Tell them all these students, all these learners, the basic concepts first, and then go into greater detail, right? Start with the physics overarching concepts as you describe, and then go to chemistry, and then go to biology. I think the reason we built up the other direction, at least in the United States, comes from the math part of it. Uh, Many of us have the same kind of frustration with math as we do with physics,
Yeah.
right? It's like, oh, this is just another language. It's just another puzzle. I don't feel connected to it. When in fact, math is beautiful. It's amazing. It's something that we humans have created in numerous different ways. And the games and the toys and the fun we have in life, so much of it is based in math, but we don't see it in the classroom. Right. And so with physics, it turns out that some of those mathematical concepts, not necessarily all the calculations, but the concepts are based in math and some complicated things that if you were trying to calculate with your hand, you might not be ready for. Right. But the concepts, if you're not doing those calculations, They're actually very basic, and they are very much foundational to other sciences like you describe. So I think in many school districts around the country, what we think is, well, we'll teach them the math so that when they get to the physics, they'll be able to do the math of the physics. And what happens is that they lose the beauty of the physics in the process, kind of get lost in the weeds to some extent, right? Instead of trying to play a game of baseball, you instead wind up spending your whole time looking for the ball in the tall grass, you
Yeah.
know? So that's the kind of thing that we maybe be able to work on. If we could find a way to flip it, just as you say,
Yeah.
maybe we would all feel a lot more comfortable and happy about science, learning it from concepts down to details.
So not to beat a dead horse, would it be easier to do something like an intro to physics and then work into a biology, chemistry, come back to it and do a more advanced physics or quantum physics?
Yes, that's
Oh,
exactly what I would advocate. I think that's a great idea. The If you can split up curricula in that way, right? Throwing physics or even biology and chemistry for that matter, right?
mhm.
Any kind of science, environmental sciences, astronomy, you you can start with basic ideas that get people to understand this is cool, this is fun,
Yeah.
and then go back and say, okay, you want to know exactly how the sun shines? Here's the quantum physics behind it. Here's the nuclear fusion. Here are the equations. Here are the thought processes. And if you want to know how Earth moves around the sun, here is now the gravitational calculations that Isaac Newton did, and then the general relativistic corrections that Albert Einstein did. And these words, instead of being like, oh my gosh, they're so foreign, I have to keep them at arm's length. Instead of you're like, oh, that's cool. Tell me how these advanced things explain these cool things that I've been dealing with all my life, or as a child, or in my beginnings of learning. I would love to see that kind of thing happen. Can you help us push some of that curricular reform, Tim? I would love that.
Yeah, absolutely. I mean, it to me, it seems so simple. It's funny. We were talking off air, and my listeners know this. I have Charcot foot. I go to the doctor every week. And
Mhm.
this time today, I went before our sit down today. And I was talking, it was a nurse only appointment. And believe it or not, I have one of the most brilliant nurses
Mhm.
on the planet. And
Yeah.
he and I are sitting talking today. He's quoting Tesla. And I know you don't get too many nurses that quote Tesla, but he was talking about, if we didn't think of things so much as atoms and neutrons, but thought of things as wavelengths and I'm trying to remember the quote, but he's going on, and I went, wait a minute, say that again, because I'm half asleep, to be honest with you, at the time.
Mhm.
But I was telling him that I was having you on the show, and that we're going to talk today, and he's absolutely fascinated, and he wants to sit in on the interview. He wants to cut work and come with me. Um, but but so we got talking about the subject before I even sat down with you today, and he was kind of the same mind that he said, you know, he's always been fascinated with astronomy and the stars, and with more wavelengths and the things that are associated with quantum mechanics, quantum physics, and
Mhm.
wonders why that isn't taught before chemistry and biology. And we
Mhm.
got into that discussion. And I said, I think maybe I open up with Dr. Liu with talking about that, because it
Yeah.
seems to me that it doesn't make sense that it gets taught out of order
Yeah.
almost.
It's time now. I mentioned earlier, it's the 21st century. We now have so much in our lives which is dependent on, based on, developed from quantum physics and quantum mechanics, that I think that we are ready to receive that information, the overarching concepts of it, right away. It's kind of why I wrote this book, the Handy Quantum Physics Answer Book. Normally, you think of quantum physics as this deep thing, right? That's just we're
Yeah.
talking about. Why
Yeah.
is you mean you can have a handy quantum physics answer book? I say yes, absolutely. The the phones that we use, the computers, the cell phones, even the way the sun shines, very basic things are all we now understand based on quantum physics. And your nurse's concept about fields and wavelengths, that's quantum physics too, and it's completely valid. Every particle in the universe can be thought of and expressed in a wave-particle duality, both a wave and a particle existing at the same time. So if you want to think about matching up or interacting fields as opposed to colliding or interacting objects, you can do that. And I think if we were to teach things that way, that might be like a different way to think about physics too. And so maybe a person, say the person we were talking about earlier,
Mhm.
who might love humor and comedy, but not necessarily love long form literature. In the same way, they might not love or be able to grasp so easily the particle-particle interactions in physics, but they could grasp the wave-wave interactions in physics. That's another way for people to access these things which might otherwise feel foreign and difficult.
So to get into the actual nuts and bolts of quantum physics,
Yeah.
what makes up quantum physics? What makes up this whole beautiful field of quantum physics? And what is it?
Yeah, that's a great question. And in fact, it's the first question on page one of the Handy Quantum Physics Answer Book. What is quantum physics? Very basically put, it is a branch of science that deals with the smallest constituents of matter and energy in the universe. We're talking about scales that are smaller than a millionth of an inch, roughly. Okay, sometimes way smaller than a millionth of an inch. In those environments, we're talking about interactions with the most basic constituents of matter and energy in our universe. And the rules that they follow, they are scientific, they make sense, but they don't necessarily make sense in our daily activity, where we're, instead of looking at one or two or a few tiny particles at a time interacting, we're talking about trillions upon trillions that have formed larger objects and thus behave differently, following different emergent principles of physics, shall we say. So quantum is like the most basic, but it's also very straightforward and simple and regular.
But there's definite rules because a lot of times we sometimes get conflicting stories in the media. So in the media, we may hear, oh no, and I'll bring up an example and we can talk a little bit more about it, maybe even a little bit later. You hear the term dark matter and you hear dark
Yes.
matter. Well, no, dark matter is mysterious and it just does this and blah, 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 blah. And you hear a 20-second blip and it seems like we don't know what dark matter is. So
Right.
then the average person goes, well, dark matter doesn't matter.
Hmm. Hmm.
That's not necessarily true, is it?
Not at all. And that's a great example. Like I said, we can, like you said, we can talk more about the details of dark matter later. But yes, what basically happened was in a classic pattern of science and scientific discovery, astronomers noticed that objects were moving in the distant universe, not necessarily in our solar system, but like galaxies and clusters of galaxies. They were moving in such a way that suggested that they were being pulled around by a lot of extra matter, like stars and galaxies or something, that we couldn't see. And they somehow considered them as dark matter. And then as people confirmed these, they started making predictions saying, well, if this dark matter exists, then it's got to look like this, right? It has to be shaped like that. And you test those hypotheses by making more observations or more experiments in your laboratory. And those predictions turn out to be wrong. And that's okay because that's what happens. You make the predictions based on some theory or some hypothesis, and they're wrong. Like, okay, back to the drawing board. What can we find that might be true? And you keep adjusting and changes until such time as you actually do confirm the kinds of things that you are speculating on. So right now, we know, based on experiments and observations, that this dark matter does not consist of protons and neutrons and electrons. The kinds of particles that we are sure that we're made up of, right? And
Okay.
so we have to look for different kinds of particles, things that would behave in the quantum realm or in our regular universe in ways that protons, neutrons, and electrons would not behave, and yet still exert or be influenced by gravity the way that protons, neutrons, and electrons would. And so there's the mystery, right? It's not woo-woo mumbo jumbo. It's actual, like, this we know dark matter is not. But what is dark matter? And then we keep working at that more and more and more. And we have now found that for every pound of regular matter, us, protons, neutrons, and electrons, there are 4, maybe 5 pounds of this dark matter that's made up of particles we have yet to discover. That's a frontier of science, right? That's not just we don't know. That's the cool stuff that we can look for.
Wow. Look at that. See, there's again, and this, folks, this is all the stuff that, and a lot of this stuff you can find, not a lot of it, all of it you can find in the Handy Quantum Physics Answer Book, which again, we have a link to in the description of this program. Dr. Charles Liu has written all of this down for you so that you can find it. Of course, we're not going to cover all 481 pages today in today's program, which wish we could, but in order to do that, we'd probably have to do a series and not just this one podcast. Dr. Liu, there's so many different topics I'd love to cover today, but I think we're getting an idea of the basics of the way things work. But not only do you have particles, but then you have wavelengths, right? So
That's right.
explain to us, there's particles, there's wavelengths, and what else am I missing that interact with each other in quantum physics?
Oh, wonderful. You're alluding to quantum field theory now.
Yeah.
So I'll start from the basics and sort of move toward that
Okay.
mumbo jumbo sounding term, which actually isn't mumbo jumbo. It's actually straight up.
Okay.
Um, One of the basic tenets of behavior of tiny particles at the small scales is that you start not being able to tell at any given moment whether or not something is a particle or a wave. Okay. In other words, if a piece of light is coming from that lamp over there toward my eye, I can equally consider that piece of light as a particle, a photon that's coming toward my eye, or a wave of energy that's being carried by electromagnetic fields into my eye.
Hmm.
And both are equally valid. You get to the point with quantum where if you try to measure it as a particle, say, how much energy does this particle contain? You can do it. But if you use a separate experiment and say, well, what is the wavelength of this light? You can do that too. So they're not mutually exclusive. This is one of the things that we as humans sometimes think. Matter is matter, energy is energy, particle is a particle, a wave is a wave, and you can't mix the two, right? But in the quantum regime, in this tiny millionth of an inch or smaller environment, they start getting fuzzy, okay?
Mhm.
And so, 100 years ago, when scientists were trying to figure this out, right? There were some scientists like Albert Einstein who said, you know what? This really looks like a particle, this photon, this piece of light. Whereas someone like uh, Erwin Schrödinger, after whom the famous cat is named, said, no, you know what? I can describe every particle as a wave. And I can think of all of the stuff coming together as waves, overlapping. Like if you threw a handful of rocks into a pond and all the waves are interacting, I'm going to think of the interaction of these subatomic particles as waves overlapping. And lo and behold, if you zoom out and look at the pond and see the whole pattern, something emerges which interacts with our lives. Maybe it's the picture that we see on the wall, or maybe it's the heat that we feel from the sun in the summer day, something like that. And that's how that comes out. And that's the wave particle duality which we mix. When you're talking about particles and waves mixing together, interacting, we then now step out a little further and say that that bigger picture, uh, there's a field in which these things are interacting. So an electron, for example, one of these things that carry electricity, it isn't just a piece of electricity or a piece of matter. It has a field around it, and its field interacts with other fields. So, when I'm pressing my hands together or something like that, it's
Yeah.
not that the particles in my skin are touching with other particles in my skin. It's the fields of the subatomic particles and the atoms and so forth that are interacting with the other fields and therefore keeping me from being able to push my hands through one another. But then it gets even more exciting because if you start studying with the fields, you realize, well, you know what? Every once in a while, under the right circumstances, maybe you can have an overlap, right? Just like those pebble pond waves, they
Yeah.
overlap. Maybe these particles on that quantum level, that tiny level, can overlap a tiny little bit. Then we get this thing called quantum tunneling. And that quantum tunneling is what leads to things like nuclear fusion, which allows our sun to shine, which gives life on their entire ecosystem here on Earth. So it's really cool how all these things interact. And you think about the interactions between these things, which seem kind of distant, but when you put them together in a coherent theory, confirmed over a century or more of experiments and further hypotheses and falsifying and confirming things, you get quantum physics. It's awesome.
It is awesome. And with that, you know what? There's quite a few theories that I want to throw your way, and
Okay.
I want you to. And here's the challenge for the second part of our program. I want you to explain how um in a quantum universe or in a quantum theory you can explain them, because a lot of our I think a lot of our, I'll put it this way, a lot of our universe here in the paranormal universe tends to have the wackiest theory as to how this happens. None of it's scientific.
Hmm.
So I'm wondering from an actual scientist how you can explain to us how, with real science, something like this could happen. But first, I want to ask you this. Now, I want you to explain to people. We hear about the double slit experiment quite a bit.
Yes. Yes.
Explain to people exactly what the double slit experiment was and how it worked as far as quantum physics.
Sure. The original double slit experiment was done by a guy named Thomasyoung. He was actually, he did a whole lot of stuff. If I remember correctly, he actually helped to translate the Rosetta Stone,
Mhm.
the original one from a long time ago. And what he did was he took a shallow pool of water, like a basin of water, and he started just pushing on one side of it, like up and down, so creating waves. And you put further away from those waves, two slots, two slits literally in a barrier. And so when the waves hit those two slots, they come out the other side in a pattern, right? And so the double slit experiment shows that when you send waves toward a double slit in a screen, you wind up with a pattern of constructive and destructive interference, the sort of black and white patterns that you often see in pictures and so forth. Now, more modern experiments, they take that double slit and instead of sending just waves of water at it, they send subatomic particles, electrons, for example, or photons, waves or particles, shall we say, of light or electricity, and they head in that direction. And now it's much more sophisticated. It's much more carefully controlled. These slits are now, instead of several inches apart, they're very, very close to each other. The screens, instead of just being, say, something like what you might see in a movie theater, they're very sophisticated detector systems. But you're still trying to do that same experiment, but instead you're doing it with subatomic particles. And so what we find is that depending on how you set up your screen,
Yeah.
whether it's detectors or whether it's something that you can see both particles or waves, depending on what you see. That wave particle duality that I mentioned, that we talked about in quantum physics, is confirmed using this double slit experiment. And you're still doing experiments to try to see, well, does it actually matter? Does when you fire electrons or electric field or whatever in the direction of the double slits, does it already set itself? Does it have to be a particle or wave when it hits the screen? Or does it have to be a particle wave when it hits the slit barrier? Or can it change back and forth at different times? And it seems that it doesn't matter what time you send it or what you do. What you decide to do in detecting it is what it turns out it manifests in our observations. So it's really cool. It's a very clear confirmation of the wave particle duality of quantum physics.
Very cool. Okay, so before we go to break, I have to ask you about the CERN reactor and what
Sure.
it is they do in a quantum sense, because they are smashing atoms together. They are sending down a huge pipeline. They're putting these atoms together, and there's everything. I mean, there's every irrational fear from they're going to open a huge portal to they're going to swallow the earth over there and
Right,
for
right.
Europe. What is it, to your understanding, and what is it that they're doing over there that is, in a rational sense, what are they trying to accomplish over there?
They're basically trying to figure out how matter and energy can originate and interact in high energy environments. There was a particle physicist colleague of mine who made a great analogy once for me and really helped me understand what they're doing in places like that. Imagine if we lived in like an icy world, like in Antarctica, but even colder. Okay. And all of the H2O that we see in our environment is ice, right? Different kinds of ice. They might be snow, they might be hail, they might be little crystals, or they might just be huge ice sheets. All right. Well, we want to understand this ice. What is the basis of this ice? And so you take a snowball and you throw it against a wall.
Okay.
Okay. And it shatters, right? Sometimes the snowball will go poof and they'll just shatter. But if you throw it harder and harder and harder, all right, then maybe what happens is that for a moment, that ice melts and you get water for a brief moment, or you get a puff of smoke or steam, something like that.
Mhm.
Okay. And before it freezes right back up again, right?
Okay.
Now take two snowballs and throw them at each other. So you're adding speed to speed in opposite directions. And that collision, for that brief moment, maybe you get lots of different particles. You get different kind of water particles, you get water vapor, you get this, you get that, and it sprays outward. And if you can take a picture of that or capture for just a moment all of those different kinds of water, could be water vapor. Now you're starting to see the nature of the H2O. All right. So that's what's happening, but on a matter scale at CERN. Okay.
Okay.
Underneath the European mountains, what they're doing is they're taking blobs of mostly protons, but other kinds of things, nuclei of different kinds, send them in one direction at close to the speed of light. Then they send another blob in the other direction at close to the speed of light. And at controlled intervals, where they've set up sensitive detectors, basically, photograph equipment, but for this high energy stuff. Right there, they will smack these two, they'll guide the collisions to happen together. And at the 99% the speed of light relative or whatever, there's a very powerful but very tiny collision. So there's no portals are going to be opened up, right? In the same way in our world, you can imagine if you're throwing snowballs at each other, you're not going to suddenly cause the entire world to become a blob of steam or something, right? Uh,
Okay.
by the same token, these collisions aren't really going to do anything to the outside environment. But when they hit, they spray out a whole bunch of elementary particles and energy pieces and things like that. And if you capture them very quickly in like a snapshot, you go back and analyze that snapshot, then you can see, oh, this was this kind of particle. Oh, that was that kind of particle. Oh, this is something we don't understand. And you explain or try to set up these experiments to try to confirm or falsify hypotheses that were set up sometimes years or decades ago. Say, if the energies are that high in this explosion, we should see these kinds of particles appear, right? That's what they've been known for. And it is exactly that we were able, for example, to confirm the existence of what we know as the Higgs particle, the
Yeah.
thing that
Higgs boson.
transfers material and turns it, creates this thing we call mass, makes things heavy. That's an example of the kinds of things that are going on in CERN. It's just a lot of fun, little kids, physicists throwing itty bitty snowballs at each other to see what comes out when they hit. That's what it is.
That's an excellent explanation. That's perfect. Okay, so there you go. There you go. So there's not going to be a giant portal opened. We're not going to have aliens fly through it. We're not going to be taken over by another civilization because we're smashing atoms over in Europe.
That's completely correct.
And it's not run by Satanists.
No, it's not.
Okay, be
It
done.
is run by
Okay.
scientists just like me and you,
Okay.
curious folks that liked throwing snowballs at each other when we were kids, and now we like throwing chunks of atoms,
Okay.
ripples throw at each other. That's all it is.
See, we killed a bunch of myths in the first part of the program. Wasn't that fun?
Love it. Love it.
All right. So we'll take our break right here, Dr. Liu. When we come back, I want to start to talk a little bit about some of the things in space. We'll talk about some of the things in space, and I want to get to the afterlife.
Okay.
There's actually something that came across your press release that talked about, can your cat be dead or alive at the same time? We'll get to that. We have a lot of pet lovers out there that would like to know that, I believe.
Mhm.
But I also want to talk about something that was a bit of a blurb about 5 years ago, and it became kind of a catchphrase. And I want to ask you I want you to kind of retain this for a bit and think about it for a bit here, Dr. Liu.
All right.
Can science actually believe in an afterlife?
Mm,
Because quantum physics has now entered the conversation, and quantum physics has now become a catchphrase when it comes to the afterlife.
mm.
And there's become the catchphrase of quantum afterlife. In other words, a pocket dimension where quantum physics has now taken over for quote unquote heaven.
Oh my.
So, and it's become all the rage on the paranormal talk circuit. So
Wow.
there have been people who have gone onto the paranormal talk circuit and are talking about a quantum physical afterlife, where essentially, if energy can neither be created nor destroyed,
Mhm.
it has to go somewhere. So it has to go to, of course, this quantum physical spot.
Wow. Well, I'll see what I can do.
All right. All right. So think about that for a bit. We're going to take our
Okay.
break. When we come back, we'll talk to Dr. Liu about some different things. We'll even talk about time travel, because time travel has to come up here as well. So the Handy Quantum Physics Answer Book is available right now. We have a link in the description of this program. We want you to go get it, because everyone should have a copy of this on their shelf. What are you going to tell your kids when they ask you basic questions? I mean, I know you're not going to answer it. Dr. Liu has. He's put it in this book. So, in fact, you have a picture of a cat right there on the cover. So
Yep.
you'll be able to
That's the
tell them.
guy. Yep.
Yeah.
Hmm.
So you'll be able to tell them what happens. So go get it right now. When we come back, we'll ask Dr. Liu about time travel. We'll ask him about an afterlife, and we'll ask him about some of the different things that are going on in the universe, including, you know what, we may even talk about black holes if we have a chance,
All
and
right.
about hawking energy, which is an interesting theory in itself. I was fascinated to read about hawking energy in this book.
Mhm.
We'll
Mhm.
explain what hawking energy is, and when we come back as well. Dr. Charles Liu is with us. When we come back, all of these things and more. Quantum physics, right here on Darkness Radio. Welcome back to the best in paranormal podcasting. This is Darkness Radio. I'm your host, Tim Dennis. Dr. Charles Liu is with us. We're talking quantum physics. The book is amazing, folks. It's one of those books that, by gosh, if you don't have it on your bookshelf, I don't know what you've got on your bookshelf. It's probably comic books, maybe a few manga novels. I don't know. You might have a few newspapers, but they don't have anything in them. It might be the shopper, the county shopper. I
Yeah.
don't know. Not a lot. Um, the Handy Quantum Physics Answer Book is the name of the book. You should have it on your shelf along with probably some encyclopedias, probably something to, point out things to the kids. I know you have the internet, but nobody believes the internet. Let's face it. It is an amazing book, folks, and a book that, let's face it, if you're a paranormal investigator and you claim that you use science in your investigations, you need this. It has some very basic answers in it. And as someone who strives to expand his knowledge base, I'll tell you, this expanded my knowledge base by quite a bit. And I'm always looking to expand my knowledge base. And even now, just in the first 30 minutes of this program, Dr. Liu has expanded my knowledge base quite a bit. So let's expand it further, Dr. Liu. Let's
Thank you.
let's talk about, let's see. Where do we want to go first? You know what? Let's talk about time travel, because it
Okay.
seems to be one of those things that we watch TV and they make it so simple, right? You throw down a little slider pad or whatever, somebody steps on it, boom, they're in another dimension. Or,
Right.
quantum leap. There's a
Mhm.
good one,
Mhm.
right?
Mhm. Yep. Yep. Yep.
You body slide or whatever, they make it look so easy. But from a quantum perspective, from
Mhm.
reality, let's talk
Yeah.
about reality.
Yeah.
Is it possible to time travel using quantum physics?
At the moment, no. What the reason I say at the moment is simply because, as with any branch of science, there's still research happening, right? So I don't want to make anyone think that you can't wonder and think about things. You so kindly said that this book is already expanding your horizons. That was really a big motivation for writing the book. People to think about and know stuff so that they can think even further. I mean, even Albert Einstein, especially, he said, knowledge is limited because it's based on what we have experienced before.
Mhm.
You need to imagine things that could be true, and then you can explore and investigate based on things that we know already to see what else is out there. So I'm always happy to talk about these things, and hopefully this book will help people get a beginning to ask about stuff. It's a handy book. It's not deeply in the tall grass yet. It's all about getting us to where we want to be. So with time travel, right, the way to think about it is that time can be thought of as a dimension, just like length, width, and height.
Okay.
But there's one huge exception to that.
Hmm.
The way that space and time knit together, we as particles in the universe can only go in one direction in time.
Okay.
Okay. Um, this is kind of a bummer, but it's a good thing too, because if we could go like backwards and forwards or in time the same way we can go backwards or forward in space or up or down or left or right, we wouldn't be able to get cause and effect straight,
Hmm.
right?
Hmm.
Um, doing a good deed here may have nothing to do with a good result afterwards. And we don't necessarily want that in our lives. We have a hard time dealing with that, right?
Hmm.
So we think of time as being able to go backward and forward in our minds, in mathematical structures, in the same way that um, if I'm counting beans on my desk, I can count one, two, three, four. I can't count -6 beans, right? But I can imagine that if I've got 3 beans now and I take 6 beans away, I actually have -3 beans, right? It's like a placeholder in our real lives, right? And
Yeah.
that gives us the opportunity to think more abstractly about how the universe works or how many beans there are in the universe and how many do I need to eat and things like that,
Right.
right?
Right.
So time is that same way here in this quantum environment. Imagine time as a thing that you can only experience going forward, but you can think about it as being negative or thinking backwards in order to think more deeply about how the structure of the universe is and how things happen. So we can't travel backwards in time, but we can certainly think about it. And one of the ways that we think about it, for example, in quantum physics, is you can think uh, of an antimatter particle as a particle that has the same sort of mass, length, width, and height, position, and so forth, that regular matter has, but you can think of its time dimension as being negative. Okay. It's
Okay.
not exactly moving through time backwards, but what it is that when you have that negative timed particle and it hits a positive time particle of the same kind, those time particles cancel out, and then you wind up with no time in which these two particles together exist as an entity. It has become energy.
Ah.
So that's an example of how you can think of antimatter or think of time as a backwards thing. It's really just we're able to travel forward, but we can use it as a tool to imagine how we can think about backwards time. If that makes sense?
Yes. Now, whenever you see stories of time travel, you see it as one of two things, either a physical travel or a mental travel, someone going within themselves and using the energy of their mind to travel and then jump into another body.
Right.
Is there something to be said for using the power or the energy of the mind to travel through time? Is that a possibility?
At the moment, again, I would say no. Our experiments just don't have enough sensitivity. And I know that people have tried. They see, like, do thoughts, for example, contain enough energy or something to allow it to travel uh, outside of our brains in a way other than, say, speaking it or writing it or something like that. At the moment, no such evidence exists. People have measured and tried to see if there's that, and there's just nothing that's been measured. The idea of quantum physics affecting or helping to create the existence of the mind or intelligence or awareness, that is still in the theoretical realm. People are making calculations and say, well, if that's true, then we should be able to find this energy release or be able to have this kind of evidence, and we haven't been able to do that yet. I think somebody, it might have been Stephen Hawking, that actually did a kind of an experiment. Something with newspapers. He put a classified ad or something in a newspaper,
Mhm.
and then many decades later or years later made an announcement, say, "Hey everybody, I put a classified ad in the past. Let's have a party." And if there was a time travel able, then at that time in the past, the party would have happened, but nobody showed up.
Ah,
So that's an example of people trying to test whether or not we can actually have backwards communications in time, especially in the far future. And it didn't happen.
okay. I want to piggyback on that thought with the power of the mind, and I want to talk about the power of intention, whether
Mm,
it be with meditation or prayer.
right.
Now, on this program, we do prayer and healing requests.
Yes.
We've seen amazing things with people getting together in the hundreds or thousands and being able to pray for or put good intentions out for, whether it be, you don't have to necessarily be a believer. You can be an atheist and just send out good thoughts.
Mm.
Um, but just putting the power of intention out for someone who may be ill, or putting out, or someone who's going through a bad time, and just say, I hope that somebody's it gets better. What does quantum physics say about a group of people putting out that type of intention to someone and putting that type of power behind someone? Is that power of the mind possible in a quantum realm?
I would say at this point, there is no way to be able to confirm that. I don't think. Okay, let's think a little bit about the amount of power involved, right? The energy in our physical world that our minds and our brains work, right, is not that big. The human brain is actually a very efficient user of electricity. The amount is less than, for example, a typical desktop computer that runs all of our stuff. If we put all of that energy in good intentions and at mind power and try to broadcast it, it would be weaker than the weakest radio signal, right? You
Okay.
couldn't get that energy from one place to another. Now, that said, I know about people who have experienced positive feelings and so forth. And that might not be in the realm of quantum physics, but more in the realm of consciousness and psychology. Okay, the human brain is a very powerful thing. We have only just begun to understand the complexities that are involved. The quantum processes that are the atoms and molecules in our brain have led to this non-quantum, right? This classical physics structure known as the human brain, which is amazing. It can receive stimuli and it can produce results in a human body that we never thought were possible, right? It's just not the way that we think that it works. So I know that some experiments have been done, not quantum physics, but sort of more like in terms of medicine and things like that, which have shown that if a person knows that other people are praying and wishing for their good recovery,
Mhm.
that they tend to recover a little bit better, a little bit faster. But it's not the energy that those folks are producing that's causing this healing. It's the fact that the person knows those positive feelings are coming, or that there are people who are hoping for this person's recovery, that causes that person's brain to act differently toward your physical body itself. It's really quite amazing. Studies are now showing conclusively that one of the biggest predictors of whether you stay healthy and strong and happy going into later years, aging for decades, is if you have a strong social network. If you have friends, if you have people that you can rely on and you get together with, or family. And so our brains do react to knowing that we have friends and that we have people who are thinking about us, not on the quantum level, but on a psychological level. And that psychological level can lead to better physical health outcomes. The statistics are still kind of, whatever. We're not able to say for sure that this always happens when that occurs. But we do see some statistical evidence that we want to have these strong social connections, and we want to have people thinking positively of us, because that actually stimulates our brains and our bodies to be well.
All right. I asked you to think about this before the break. And
Yes,
that is
I've
the,
been trying.
the,
The smoke has been coming out of my ears on this.
about the quantum theory of a soul and the quantum theory of an afterlife, the place where the soul would go.
Right.
In your education, in your experience,
Mhm.
and in everything that you've learned, do these add up? Does this make sense? Is it something that could fit into your realm?
Mm. Great question. And I'll use your term. Do they add up? At the moment, they don't add up.
Okay.
People who are doing the scientific investigations of trying to figure that out, they do very careful experiments of trying to see, for example, is there a difference in the mass or the energy levels of a person who we consider to be alive compared with that person if the person has died? Or is there that soul? Is there that consciousness, that kind of thing? When people try to measure energy levels or whatnot, mass levels, nothing adds up. So that's not going to be the way that we can find the answer to that at the moment. Now, what we don't know yet, and here's where maybe you can start thinking along the lines of afterlife or whatever, right?
Mhm.
Is that quantum mechanics predicts the possibility of multiple parallel universes. All right. These universes cannot interact with one another, as far as we know. They cannot overlap. So you can't slide from one universe to the other, at least based on the physics that we know now.
Okay.
But there are two general ways which scientists think that could lead to many different universes existing, many different instances of space and time that exist. On different axes or in different dimensions. And these two methods may allow for the existence of something that we might recognize as an afterlife, just not the way that we've envisioned it in terms of either our religious texts or our ideas of science and trying to solve them. It's a different thing. But something different from our universe may exist. We just have no way to test that hypothesis yet. We don't have the technology.
Okay. I'm going to bring it back to this plane.
Okay.
You have many people who have of sound mind, of sound body, not in a dream state, anything like that, have seen a full body apparition of a ghost
Yes.
that stands in front of them, is interactive with them. From a quantum standpoint, how do you explain a full body apparition ghost?
Great question. Quantum physics cannot explain at this time a full apparition ghost. There just isn't, like I said, enough stuff that adds up. The full quantum apparition ghost view also is, I still go back to the human brain. And again, since I'm not a psychology researcher, the specific numbers and the values are not at my fingertips. So I apologize for not being able to produce
No,
that.
that's fine. That's
Uh,
fine. I haven't given you enough
no, that's okay.
of
But
information or anything like that in order to break everything down. But
yeah,
um, I mean, yeah, I mean, obviously, you're not in a situation where you can break everything down in a room and be able to tell me exactly
right,
what stimuli could be there in order to produce such an apparition. But
right.
because every scenario is different, but it's a common, should we say, phenomena? It's a common phenomena, especially not just with people in the paranormal field, but I mean just with people in general. I mean, you
Yes.
see people who, I mean, my own grandmother, for example. Um, she's although in this case you could say it was a could be her coming out of sleep, but she feels a tugging at her toes.
Yeah.
Feels her
Yeah.
toes being wiggled. She wakes up, looks at the bottom of her bed, and there's her sister who's been passed away for 10 years.
Yeah.
Her sister Joanne wiggling her toes and saying, Susie,
Wow.
come on, get up, get up. And it's the same thing she did when she was there in life, but looking like she looked at the prime of her life.
Isn't that something?
Yeah.
Our human brains are amazing. I wouldn't put it past anybody's brain, including your grandmother's, the ability to have that experience and be in your brain as real as any other experience, and yet not have the external matter or energy flows that we would otherwise be able to detect,
Mm-hmm.
right? Um, there is my favorite line in the Harry Potter novels. All right. I didn't read all of them, but one of my favorite lines I read was in the last book where I hope I'm not spoiling anything for anybody. Uh, Harry Potter asks Dumbledore, is this all real or is it all just happening in my head? And Dumbledore replies, right? Of course it is all just happening in your head, Harry. But why on earth would that make that any less real? Right. And so what we can say is that the human brain has such complexity and such beauty in it that we can hold many ideas in our head at the same time, and we may be very much experiencing something that is real to us, but other people cannot detect, right?
Mm-hmm.
Uh, there are plenty of people, like you said, and it's very true, in real life, without being in a dream state or without being in a drugged situation or anything like that, their brains, the conscious part, not just the unconscious part, can make you think or see objects, visual or hear things, or taste things, even smell things that are not there from anybody else seeing them. But in your head, they are as real, or they can be as real as smelling a real rose, or tasting a real pretzel, or seeing a real human being. So I would look in that direction in terms of the not quantum, but the non-quantum effects of a complicated, sophisticated organ and a body, an organism, as the human and the human brain together to look for those explanations.
But when we come to things like shared death experiences or things where, like, let's say, I don't know if you've heard of these type of experiences before, Dr. Liu, but like someone receives multiple telephone calls from the dead. Like, let's say you and I have a common relative in common where they just pass away. You get a phone call from them. I get a phone call from them, and they're just moments apart.
Yeah.
I mean, obviously, that's not in your head or my head. Where is that coming from? Where's that energy coming from?
Yeah. With phenomena like that, I don't know how we can make a good scientific test, right?
Right.
The way that scientific tests work is we think that this theory explains something scientific, that something that's happening. So we devise a circumstance where we control for random things and then see what happens. So we might say, for example, okay, in that circumstance, I'm going completely out on a limb here. This is
Sure.
not the quantum physics, but imagine, say, I want to test if that's true. And so I have a relative, a dear friend of yours, who is soon to pass away and wants to participate in such an experiment. And he says, okay, if such a thing can occur, the moment that I pass away, I'm going to call you both. Okay.
Mhm.
And if you do both receive the calls at the same time, now I'm going to tell you that's going to happen, then that's a experimental confirmation, right? If, however, that person passes away and we don't receive that, then that's a falsification, right? That has not been converted. Therefore, this guess or this technique is not a way that we could have tested that hypothesis, and it's not scientific if it happens.
Yeah.
So explaining things after the fact is a lot less confirming from a scientific theory perspective than setting up something ahead of time and then testing it afterwards, right? This is a thing that happens so often in the history of physics. How the sun shines, for example, a very famous astronomer Lord Kelvin, William Thomson, Lord Kelvin, after the temperature scale is named after,
Yep.
right? He made a prediction. He said the sun shines. This is in the 1800s. He said the sun shines because it is shrinking and it's falling. The outer layers are falling down on top of the lower layers, and that kind of falling is actually releasing energy. And he made that hypothesis, and they made calculations, said, well, you know what? You can produce that amount of energy with this kind of technique. You just have to show that the sun and the solar system is younger than about 10 million years. And then what happened was decades later, we showed through radiocarbon dating and things like that, that the universe, that the Earth specifically, was billions of years old as opposed to millions, and therefore that hypothesis was shown to be wrong. His prediction was not confirmed. Turns out, though, that falling physical process is real. It actually does work, and in fact, it helps power supermassive black holes, quasars out deep in the reaches of the universe, because it's material falling down onto the surface of a black hole that causes them to shine so brightly. In many cases, they can shine in 1 second more energy than the sun would shine in millions of years. So the hypothesis, the way of trying to solve that particular question of how the sun shines was wrong. But the process of trying to confirm and prove or disprove the way the sun shines led to even more deep discoveries about the universe in different ways. That's the kind of thing that maybe we can try to work for in these kinds of questions.
Interesting. So I got to ask you the question, how can your cat be dead and alive at the same time?
Yes, this is called Schrodinger's cat, right?
Okay.
And I mentioned Erwin Schrödinger earlier in this hour. We had a really fascinating discussion back in the 1930s or so, 20s and 30s, between Albert Einstein and Erwin Schrödinger and a bunch of other scientists. They were trying to understand this wave-particle duality thing. How can something be both a wave and a particle at the same time?
Mhm.
Okay. And so Erwin Schrödinger said, well, let me give you a thought experiment on how something can be both alive and dead at the same time. Okay. Imagine that you have a cat that's in a sealed, airtight box. Okay. The cat has plenty of oxygen to breathe for a period of time, but there's a little poison capsule attached to a quantum device. This is kind of cruel,
Oh,
but
yeah.
we wouldn't do this in real life at all,
Oh,
right? This is
okay.
completely a thought experiment. He
Okay.
said, what if there is a quantum probability, all right, that this quantum process will happen? If the process happens, then the poison is released and the poor kitty meets its demise. But if the process doesn't happen, then the kitty is fine, right? But you don't know till you open the box whether the quantum process has happened and whether the kitty is alive or dead. So while it's closed, is the cat alive or dead? And so what Einstein said was, well, we can't know, right? But what Schrodinger said was, instead, why don't we say that if we know that there's a 30% chance that this quantum process will happen, this decay will occur, or this spontaneous thing will happen. If we know it's a 30% chance that it will occur, then we could say that until we look, the cat is 30% alive or 70% alive and 30% not alive or 70% not alive. You see how you wind up with a partial, both alive and dead at the same time idea, right?
Mhm. Mhm.
And this is the concept of Schrodinger's cat. It foresaw what we call today quantum entanglement, which suggests that until you look at a particular quantum system, you do not know what it is, alive or dead, or zero or one, or whatever you want to do. It's not a binary one or the other. It's some mixture. And so we can use that mixture in a mathematical way or in a computational way to do things on a very, very fast time scale until we actually measure or until the quantum state collapses or whatever, and you see whether it's a zero or a one, or whether the cat is actually alive or not alive. That's the cool part of the Schrodinger's cat.
So I have this question for you, Dr.
Sure.
Liu.
Uh-huh.
I want to switch things up and get a little more celestial, a little bit more out there into the galaxy.
Sure.
If time travel is impossible. Is it possible? We hear about wormholes all the time, and that
Right.
wormholes may potentially be possible. From a quantum standpoint, are wormholes a real thing?
From a quantum standpoint, wormholes are mathematically possible,
Okay.
right? There's a difference again between the being a real thing in our universe and being mathematically possible,
Okay.
right? And very often one leads to the other, but that doesn't mean that they always happen, right?
Okay.
So wormholes are an example of that. Einstein basically created this wonderful theory we call general relativity, right? And this system is based in part on a system of 16 equations that all have mathematical implications. And what Einstein was trying to do was to figure out of these 16 equations, which solution to these equations, which are very complicated, which solution correctly represents our universe.
Mhm.
Okay. So there should be just one universe, right? And so we have in the past 100 years or so found solutions to Einstein's field equations that seem to imply our existence in our universe being what it is. But those solutions sometimes have other consequences, right? In other words, yeah, we see that our universe is doing this and has this kind of space and time characteristics, and this is how gravity works. Great. But you know what? If I look at the mathematical solution here and look at it carefully, holy moly, there's a possibility that there are places in the universe where there is no volume, but there is mass. So you wind up with these singularities, which in math happens all the time, but in real life doesn't seem to happen much at all. So decades ago, people said, you know what? There are some singularities in this. Do we have such singularities in the universe? Well, most kinds of singularities we have not been able to find, but we did find a couple of singularities. One is black holes. Black holes can be thought of as having a singularity at their centers where there is an infinite density and there's zero volume, right? Which is kind of cool.
Yeah.
Um, the black hole itself as an object, right, actually has an event horizon within which we cannot pierce. We can't see what's going on inside them. So we don't actually know if the singularity exists in there or if it's just mathematically the result of the equations. But the possibility does exist, right? Another singularity that we figured out is the beginning of the universe, the Big Bang. At that time, as the time or the age of the universe approached zero, the volume of the universe approaches zero, which means that the density of the universe approached infinity. And that's a singularity too. And people are like, really? Is that how the universe works? Turns out that was discovered. It was confirmed that indeed the universe was once very, very small and now is very, very large. So at some point, it may well be that those equations predicted the singularity that we know today as the Big Bang, which caused the creation of the universe when time started to run forward. So scientifically, these singularities did turn out to exist, even though mathematically many singularities were predicted, and only these two so far have been found. Others haven't been found yet. A wormhole, to make a long story short, is the manifestation of such a singularity in mathematics. So we could find their existence, but we've looked, astronomers have looked and looked and looked and looked, and we have not yet found a wormhole. Does that make sense? They could exist, but we haven't found them yet. So we don't think that they exist in the way that we'd like to. In the quantum realm, if a wormhole does exist, it probably can only send subatomic particles through, a few at a time. Being able to send like a whole spaceship through or a human being through doesn't seem possible at all.
With the new telescope, there was an article that said that eventually it'd be able to look. Does this? It did. This didn't make sense to me at time. It'd be able to look backward in time, be able to see the eventual beginning of the Big Bang. Explain this theory to me.
Ah, okay. Yeah, this is complicated and it is often incorrectly represented in the media. So
Okay.
let me explain this concept. Um, there's a thing called look back time that we use in astronomy all the time, but it happens in our lives too. Um, if I am right now broadcasting with you
Yes.
over Zoom, you actually aren't seeing me instantaneously the moment that I say something. In fact, the energy needs to go through the air, the whatever I say, then through the electronics, and then through different things before it comes in to your microphone
Mhm.
or headphones. So what that means is that there is a delay, a time lag. You're seeing me as I was a fraction of a second ago.
Yep.
And I'm seeing you as a fraction of a second ago. Now, that's no big deal for us because we humans, we talk on the time scale of fractions of a second.
Mhm.
So I don't think that you're like way in the past. But if you imagine a time lag, if we were billions of miles apart, our light signal has to travel those billions of miles, get to you, and then you have to say something, and then it takes billions of miles to come back to me. That's a real time lag. And that could be, in the case of the solar system, minutes or hours. That's why, for example, when we are working with our Mars probes right now, we send a signal from Earth. It takes 20 minutes at least, depending on our positions in our orbits, for the signal to get to Mars, and then 20 more minutes for a signal from the Mars probes to get back to us.
Ah.
So if we tell the probe, there's a cliff coming, don't run over it, it'll be too late.
Yes.
Right.
Yeah.
So
Yeah.
that's why those probes have to be built in with sensors to sense, oh, cliff's coming. I better not go. Uh, I'm just going to send a picture back to Earth and say, yeah, here's a cliff here. I'm not going there. And then
Yep.
we find out 20 minutes later, oh, good job. Glad you didn't go over the cliff. Right.
Right.
Take that to the nth degree and talk about the whole universe. Right. And that's where we're looking back. When we see distant galaxies that are a billion light years away, right? A light year is a distance that light takes to travel through space in a whole year, right? That's a distance,
Right.
but it counts as looking back a year ago in time. Looking at an object a light year away means that I'm seeing it exactly as it is a year ago, not a fossil, not some projection, but the actual thing itself. If I look 10 billion years back, then not only does the signal take 10 billion years to get to me, I'm looking at that galaxy as it existed 10 billion years ago. Now, 10 billion years is a long time, so it's going to look like an infant, right, compared to what it is today. And then if you look all the way back, as far back as you can get, is the age of the universe.
Mhm.
So if your telescope is so good that it can look as far back toward the beginning of the universe as possible, as the physics of the universe allows, you're looking back more than 13 billion light years.
Ah.
At right. See, so that's the look back time we're talking about.
Okay.
13 billion years in time, 13 billion light years in distance, co-moving distance, in fact, because the universe is expanding. So it's really, really, fun in terms of geometry and complicated motion. But what that means is right now, our universe becomes transparent to light at about 380,000 years after the Big Bang. Okay. So 13.7 billion years and a little bit ago, that was when all the light, the photons and the matter and so forth in the universe disengaged enough so that streams of light can travel through the universe and eventually to our telescopes and our eyes. Okay. Over those 13 billion years, that light, which used to be blinding visible light or infrared or ultraviolet light, has morphed and changed over time and become microwave radiation. Okay, a little bit longer than the radiation generated by your microwave ovens in your kitchen.
Yeah.
So our regular telescopes like the JWST or the Hubble that are out there orbiting right now can't normally see it. But we have sent up telescopes that can look out in space at microwave radiation, right? You
Okay.
get away from the microwave ovens here on our ground and the
Yeah.
cellular communications and so forth, and you look out there and see what's net out in the universe. And it turns out we can see that radiation from that early time in the universe. It's called the cosmic microwave background. And that discovery was one of the most important discoveries in the history of astronomy because it confirmed to us indeed that long ago the universe was very different and much smaller and much hotter than it is now.
Wow. It's amazing.
I love it. I think it's really awesome, right? And we were talking about this at the beginning, right? Imagine if kids learned this kind of physics first,
Yeah.
right? They
Yeah.
would be, I think, much more curious and interested in learning physics and chemistry and biology in later years because they're like, wow, now I'm going to find out how the universe became what it is like now today. What is that stuff underneath? And that would be a great thing for all of us if we all were more science literate, if we all could help us answer those big questions in our lives with some more underpinning of what we know the processes and the methods that the universe behaves under so that we can get even further in studying the things that we don't understand yet.
Right, right. One more thing before we leave people today, I had mentioned Hawking energy, and one of
Yes,
the things I was reading about in your book, and it absolutely fascinated me. I remembered reading about it in an article years ago,
right.
and the fact that Stephen Hawking had brought up that energy actually seeped out of a black hole. When you think of a black hole, you think of something that things get trapped in and never come out of. But
Right.
it's possible that things escape, but it's just energy that escapes out of a black hole, correct?
Yeah, Stephen Hawking's original idea was brilliant. He basically combined uh, Einstein's general theory of relativity, which describes space and time and predicts singularities like black holes, with quantum physics, the idea that things can be both particles and waves at the same time. Okay, what the implication was is that Hawking explained that because things can be both particles and wave at the same time, that holds true for black holes too. So the border of a black hole, the event horizon, which if you don't take quantum physics into account, is a solid, clear border, either you're in or you're out,
Mhm.
becomes fuzzy. And so you could be like Schrodinger's cat, may be alive and dead at the same time. You might be in and out at the same time under the right circumstances. A tiny amount of energy, therefore, from this boundary seeps out into its environment because of quantum processes, right? You can think mathematically of it as being particles that get ejected once in a while. Another way to think about it is that just energy seeps out of the boundary of any object very, very slowly over time. So just say this computer screen, all right, this monitor here,
Yep.
energy is coming off of it because we're sending electricity into it, right? So we see stuff coming out.
Yep.
But even if you turned it off, all right, even if there's nothing going on, there's still a tiny bit of heat that's coming off of it, always, because of quantum processes. All right. And so he said, you know what? If it works for regular objects, it's got to work for black holes too. And so this is the origin of the idea of Hawking radiation. People have since made calculations. Unfortunately, we can't measure it. This Hawking radiation is so slow and it's so tiny that it would take millions of years for the Hawking radiation from even a supermassive black hole to register on any kind of telescope or detector that we could create. So it's really, really hard. But the math seems pretty solid. And what that means is that a black hole, say the one at the center of our Milky Way galaxy, right? Um, After a billion, 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 billion years, okay, sorry, I
Right.
just have to count my billions,
Oh, that's a lot of billions.
would appreciably have less mass contained in its event horizon than it currently has. Okay. And
Oh,
then if you wait another many, 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 many billions of years, it will actually have released so much of its energy in this Hawking radiation that its mass will go to zero. And so the black hole will literally evaporate. And this is something that we still haven't been able to confirm experimentally, but the math works pretty well. So most people think that that's likely to be true. And so that means that black holes aren't, say, a rip in the fabric of space-time or a wormhole, right, as we might think,
yeah.
but instead they're like water balloons or hernias. I mean, I hate to use gross biological analogies, but something that's collecting material in a pocket in space-time and then slowly ejecting it out.
Interesting.
That's That is the Hawking radiation implication for our universe, if that's true. And that's been worked on for many years. And in fact, Stephen Hawking, until his own death, was working on trying to figure out what could emerge from a black hole in the future if this Hawking radiation idea turns out to be confirmed. Yeah, it's really, really neat stuff.
Wow, that's very neat. All right. And I swear, last question.
Sure.
For the layperson out there, what is the difference between a regular PC and computer and a quantum computer?
Ah, wow. Uh, it's almost like the difference between a landline telephone and a cell phone, or more.
Okay.
Okay. Um, all right. I'll try to make it quick because it's
Sure.
complicated, but
Okay.
it's fun to
Okay.
think about. Okay. In ordinary computing, we think of ones and zeros,
Yep.
right? What we're trying to do is to send little bits of electricity through our equipment.
Mm-hmm.
1 0 1 0 1 0, and by building up many ones and zeros together in a stream, you can turn things on and off. You can send switches back and forth. Okay, I can make, for example, this pixel on my screen bright or dark, or
Mm-hmm.
slightly brighter or slightly darker, and then that sends an image, right?
Okay.
So that's what regular computing is: ones and zeros, ones and zeros, ones and zeros, and they can move very fast, right?
Mm-hmm.
Billions of ones and zeros per second can be sent through computers. And that's why, for example, our computer screens, even though they have millions of pixels in them, they can still look like 30 times a second they're changing. And therefore, it looks like we're moving because it's just taking all these pictures so quickly, right?
Okay.
So regular computing is very fast, but it has these ones and zeros that limit what it does. With quantum computing, it's like taking those ones and zeros and making each one of those ones and zero combinations into Schrodinger's cat, so
Ah,
that they could be one or zero or some combination in between until they get from one station to the next. During that time that they may be one or may be zero, if you can find some way to coax that 1 0 combination thing to do some calculation or to do something different from just sitting there and doing nothing, you might be able to harness the power of that quantum activity to create a whole set of computing strategies. So in regular computing, the 1 0 pair is called a bit.
okay.
In quantum computing, that maybe one, maybe zero bit, okay, is actually called a qubit, Qubit, meaning a quantum bit. So before it becomes a one or a zero, it can still do other stuff.
Ah, okay.
So that is where the quantum computing part comes in. We don't know yet. We don't have enough software even to know how to manipulate or to take advantage of that in-between state when that qubit is not exactly one or zero yet. But modern quantum computing is trying to utilize that space, figure out a way to use that time, really, really fast time, to make calculations that aren't even like taking billionths of seconds, but taking trillionths of seconds or quadrillionths of seconds, really, really short times. And from there, be able to solve some computing problems that current computers cannot do.
Wow.
Yeah, it's neat stuff.
It is. It is. That's amazing. Well, Dr. Charles Liu, I want to thank you so much for being on the program today
Oh,
and
Tim, thank you so much for having me. What a pleasure.
yeah, and knocking down a lot of different things from a scientific standpoint that here in the program it seems like people struggle with every day. So I mean, we've covered a lot of ground today, and I want to thank you so much for doing so.
Oh, thank you for having me. It's a real pleasure. And I want everyone who's curious and thinking about things to learn about these kinds of things that we know already so we can apply them to what we don't know and maybe gain even more discovery as time goes forward. Thank you so much for having me.
Thank you. The Handy Quantum Physics Answer book is available right now. We have a link in the description of this program. Dr. Charles Liu, thank you so much for being on the program.
Thank you, Tim. Thank you for having me.
Thank you. All right, folks, super secret second segment for today. Now that we've talked to Dr. Charles Liu, I want to thank him for being on the program today. Again, go out and get the book from Dr. Charles Liu. We're done talking quantum physics now. I want to bring in our super secret second guest today. And actually, you know what, folks, I have a really great time at the end of August every single year, Michigan Paracon. And again, go to darknessradioshow.com in the event section. Get your tickets for this event this August. And I'll tell you why. They say all good things must come to an end, unfortunately. And there was an announcement this past week that it's true, Michigan Paracon is coming to an end. Sadly, with this next year, the 2024 Michigan Paracon Paranormal Convention, Paracon, is coming to an end. And I believe it's the 15th one. I have Brad Blair and Tim Ellis on the line, and the founders of the big convention. And fellas, it's true. All good things come to an end, right?
Absolutely. And, it's been a hell of a run. And this is actually our 14th annual. It should have been the 15th. We had that little break with COVID.
That's right. That's right.
Yeah. So, no, it's been 16 years really since Tim and I sat and kicked around the idea of would it even be possible to put something like this together in the wilds of northern Michigan?
Yeah. And to be honest, Tim, it sitting here talking with you about it and hearing those words, and talking about it being the last, it's still kind of trying to let it settle in and sink in. Even for us, it's crazy bittersweet. And, we're ready to try new things and spread our wings in other directions with the time that this will free up. But man, oh man, when you start this thing as a baby, when you lay the egg and sit on that thing until it hatches, and here it's growing into this wonderful, beautiful thing. It's this is it's still getting used to the sound of talking about it being the last one.
Let me throw a little more weight on it here, because I want you guys to realize what you've built, this monster that you've created. This really is like the San Diego Comic-Con of the paranormal. This is no little thing you guys have built here. I mean, I kind of want to get your impressions here as to whether you guys realize what it is you've built here and how many lives you've touched. I mean, as the reactions are starting to come in now, as people are starting to see this on social media, as we're taping this reaction or this announcement is pretty fresh, and the reactions are pretty fresh. Have you taken just a little bit of time to register what it really has meant to people?
Well, back when we put this together, Tim, we were, of the thought process that we would maybe, if it went over well enough, going to get a 2-year run out of it. Back then, the shows like this didn't last more than a year or two. And we thought, if it went over well enough, maybe we'd get a second year. And we never thought, 15, 16 years later, that it would still be going. And, the outpouring of support and love from the community has been amazing. Yeah, it's absolutely not anything we ever anticipated this event evolving into.
Yeah, within a couple of years of it taking off, we learned quickly back then kind of what this was starting to mean to people even back then. And as they came back year after year, and we saw the people start, like, the numbers growing, and everyone saying this felt like a family reunion to them, we quickly embraced that this is what was starting. And we didn't set out for that, because we didn't know what, first of all, we didn't know what the hell we were doing. We were just trying something.
We still don't.
No.
Oh, come on.
And secondly, we didn't set out for that because we were just wanting to see what was going to happen when we tried this. And then all of a sudden we realized this was literally bringing people together who always felt a little outcast, felt a little strange in, and I'm using air quotes here, the real world, the normal world. And they found a safe, common ground to come to at Michigan Paranormal Convention, where they could share their stories and ideas, and they were embraced instead of, laughed at or looked at weird. And we quickly realized we had built something much more special than we even anticipated.
You guys say you still don't know what it is you're doing. You guys have it down to a science. I mean, you really you've got it down to from the moment you walk in, and it's just this open, warm feeling, to people coming in, meeting and greeting each other, to meeting and greeting all their favorites, to getting and seeing people speak, and I mean, they're laughing from the time they get in the door to the time they leave, and they don't want to leave. I mean, and the party gets bigger and bigger. I mean, even though on the website it says August 22nd to the 24th, it seems like people are coming in the 20th to the 21st, and they don't want to leave until the 25th to the 26th. I mean, people are, you know, their fingers are white because they're white knuckling it and not wanting to leave the casino. You know, and that's a testament to what you guys do. And again, you know, I'm not blowing sunshine up your skirts here, but okay, maybe I am. But the idea is you don't build something like that with the idea that it's just, you know, schlepped together with a little bit of spit and baling wire, and, you know, you hope people buy in. You've put together a quality product.
You know, oh, sorry, go ahead, Tim.
Oh, no, go ahead. Go ahead.
I was just, I think a turning point for us was when we realized where we had brought this and to how much the fans trusted us to put on an event that they knew was going to be of the caliber we had built it to, was when we started putting on ticket sales for the coming year, and we hadn't even announced one speaker yet. It didn't matter. People knew, they trusted us to make sure we put together that kind of an event where they were going to shell out their hard-earned money and be there regardless of not even knowing one speaker. And to that, I remember Brad and I just looking at each other like, we've sold these many tickets already without announcing one name. That shows how much trust these people have in us. Yeah.
Well, it's not just that, but you guys are a brand name. I mean, and it's not just the people you bring in, you're a brand name. I mean, look at your merchandise. Your merchandise sells out within half an hour of you putting it on sale.
It's crazy. Yeah.
I come in, I can't get a sweatshirt in my size. I tell you guys, okay, put one aside for me. It's gone. Yeah. I mean, that says something. So I mean, you know, part of the reason I wanted to have you guys in, not only just to tell people that, you know, get your tickets now, folks, because after this year, it's done. It's done. And get in, and this is going to be the biggest year ever. So let's fill the place to the rafters. We want it so full that you can't move, first of all.
Yeah.
But second of all, that we want it to be the biggest going away party of ever. You know, we want to throw the biggest thank you party for Brad and Tim ever. So let's get everybody in there so everybody can give these guys hugs. And Tara too. We want to give Tara big hugs too.
God knows we could not do this or be where we're at without Tara McLeod involved in this. She is the glue behind the scenes holding the event together quite often. Her and we also don't want to overlook the staff from the Sault Ste. Marie Convention Visitors Bureau, who we've teamed up with and have just been amazing over the years to work with. But yeah, Tara does all of the vendor setup, all of the table placement, and she is often the one that's catching the brunt of any type of complaints or anything that's, you know, runs afoul. She is everywhere, taking care of things, making sure everybody's happy, making sure the event is running smoothly. And God love her, we would not be here without her.
Yeah. And, you know, while we're definitely making sure we're naming those who deserve to be named, you know, we got to shout out to our boys, our group, the Upper Peninsula Paranormal Research Society. I mean, this event doesn't happen without hardcore volunteers, and our team has been there year in and year out to make sure this event runs. And then one of our guys, Steve LaPlante, he's in charge of getting other volunteers beyond our team. So it literally takes a small army behind us to make this run. And it has been a hell of a run and a hell of a journey. And it's the memories that we've made, you know, with our team together, working through the years, has been outstanding.
Absolutely. So folks, here's the deal. We have a link in the description of this program. Get your tickets right now. Get your airfare lined up. Get lodging lined up. Get it all lined up, because all good things must come to an end.
I'm looking for, it's going to be interesting the Saturday for people who have been there. They know what the Saturday night party is. For people who haven't been there, and if you're coming, so I mean, we have 3 different bars in the casino where we're at. So I mean, it's easy to get a party together on Thursday night or Friday night, but Saturday night, the last night when everyone's done working and we can all just let loose, Saturday night is always the big party. I can't even imagine what this Saturday night's party is going to be like when we all know that it's going to be the last time we're going to be together like that for that event. Obviously, there's other great events that Brad and I and Tim, you're involved with, that we're lucky enough to go around and be a part of these other events. And we'll see a lot of the people we see at MI Paracon at these events, but this will be the last one of ours, our home rink, if you will. And that Saturday night party is going to be bittersweet, man. And I can tell you right now, probably a lot of tears.
So what are you guys looking forward to? Brad, what are you looking forward to? Tim, what are you looking forward to? A few highlights for the weekend that you guys are looking forward to that you want to promote. Let's talk about things that are going on throughout the weekend that you guys are looking forward to.
Yeah, you mentioned lodging, Tim, and just to let everybody know, the casino is sold out for the weekend, but we have plenty of hotels in Sault Ste. Marie, and they are more than happy to help you find lodging through the Convention Visitors Bureau. If you go to SaultSte.Marie.com, the casino is providing shuttle service to all of the hotels in the area for that weekend. So all you have to do is pull in, park, get your room, and they will send a bus to pick you up and get you to and from the casino for the event. So no need to worry about self-transport once you get here. As far as the weekend goes, it's packed. We are packed. We have presentations. Of course, as you mentioned, it kind of has crept beyond just the 3-day weekend that we've always done. We'll have our pregame party once again on Wednesday night at 9:00. That's in the Rapids Lounge at Kuwaitan Casinos,
and that's free to anyone.
That is free. That is open. That is kind of a welcome in, everybody. And we've got a few of our presenters that I know are going to be on hand that we'll kind of juggle some people in, have some fun panels at that, and it's just more of a welcome party for everybody that's coming in on Wednesday or sooner. And then, of course, all afternoon on Thursday, all day Friday, all day Saturday, we have presentations, workshops, psychic galleries, and it's just such a packed weekend.
And to be honest, Tim, we as much as we love going to events like this, at our own event, we're so busy, we don't get to sit down and watch hardly any of the presenters. Sadly, we might maybe catch 10 minutes of the beginning, and then we got to run off and be somewhere else, or as I'm emceeing the event, I might catch the last 10 minutes of a talk before I got to get them off the stage and get ready to bring the next presenter on. So we just, as excited as we are about the lineup we build year in and year out, we just don't have the time to enjoy it as much as we would like to as a guest gets to. So, I don't know that I can say I'm looking forward to one presenter because I know I just don't get to see them. I do think the one thing we're going to do, can we talk about what we're doing with Ghost Hunters yet? Or not? Okay.
Yeah. No, everything's good. The full schedule should be out by the first of next week. So
So we're doing what? 20 years?
20th anniversary
of Ghost
Hunters.
Yeah.
Being on the air.
So we're going to have as many of the Ghost Hunters crew together as we can on stage. We're going to do a big panel with them and just kind of talk about the history of. And so I think that's, if this is going to be our last, let's kind of give a tip to the hat to the first TV show that really blew the doors off of paranormal reality TV, and it was Ghost Hunters. And so I think it's kind of cool. They'll be our headliners. They'll be our last ones on Saturday night. So we'll kind of give a tip of the hat to the folks who started it and really allowed us to create an event like we did.
That's completely awesome.
Yeah.
I love it. That's great. That's absolutely great and appropriate. Very appropriate.
Yeah.
So,
yeah.
Wow.
Agreed.
Oh, wow. So folks, again, there's a link in the description of this program. Go get your tickets. Like Brad pointed out, there's lodging within Sault Ste. Marie. There's buses that will run you to the casino. It's no excuse. There's no excuse. Get your airline tickets, get your tickets for the event. Come on in. It's the final one. There's no more time. There's no more time. There's no more excuses. There's no more sitting on your wallet. There's no more, maybe next year. Enough of the excuses. You only live once, as far as we know, unless you believe in reincarnation, then we may do this thing again. But as far as I know, in this lifetime, there's only this year. So come on out with myself. Come on out with Mally Fox will be there. So
Yeah.
Mally Fox will be out there. We're going to have a good time. We're going to party it up. We're going to have a great time. You're going to see any and everybody in the paranormal that you want to see. I don't know of a better reason. And of course, that wonderful way to end it with the 20 years of Ghost Hunters. I can't think of a better way. So you guys, again, have outdone yourselves. And man, I don't know how I'm going to spend August now. I'm going back to golfing in the Minnesota State Fair in August. It's depressing.
We'll find a way to trust me. Life finds a way to fill those holes. No problem.
All right. Well,
We'll all be busy enough before we know it again.
I'm holding you to it.
All right.
So, well, thank you both. I appreciate you. And by the way, I want to thank you both personally for, again, for 14 summers of the most amazing experiences, of meeting the most amazing people, of having the most amazing times. I personally thank you from the bottom of my heart for what you've done, not just for myself, but for the entire community. So thank you both.
Well, thank you for being a part of the event, Tim. I mean, it's one of those things you make these friendships with people that, way past the event being through, there's people that we're always going to be in contact with. And you can just tell that the camaraderie of the weekend is one of the biggest things that I think have brought people back year after year.
Yeah, absolutely. So, and we appreciate you and your support over the years too, Tim, and having us on your shows and helping us to promote the event as well. So thank you.
Well, it's my pleasure. And thank you both, and looking forward to a great weekend.
Yeah, we'll see you in a few weeks.
See you soon.
We'll see you.
For more audio and video archives of the show, visit darknessradioshow.com. Thanks for watching.